In this video, I'm going to give you a problem to work through, and then I'm going to have you pause it, and then you can unpause it and check your answer. So what is the pH of 0.1 molar ammonium bromide? So if you watched the last video, we went through a similar problem, but I wanted to have you go ahead and kind of stop and pause and go through this. So go ahead and pause and figure out whether the salt is acidic, basic, or neutral, and then that'll kind of allow you to hone in on which ion you need to worry about, and then unpause it and we can go check through it together. Okay. All right, so the very first thing is it acidic, basic, or neutral? So we've got to look at the ammonium and we've got to look at the bromide ion. Bromide comes from a strong acid, hydrobromic acid, so because of that, it must be completely neutral. So the ammonium ion doesn't come from a strong base, so lithium, sodium, potassium hydroxide, strontium, barium, calcium hydroxide. So that means that it must come from a weak base, which means that this has to be acidic. So because it's acidic, then we have to be writing down the Ka reaction. So NH4 plus K plus water is in equilibrium with NH3 plus H3O plus. All right, so we know that this is the reaction that's going to allow us to figure it out. So go ahead, and if you haven't done it yet, pause the video and try and fill out this ice chart and see where you go. There's a little hint. There's a table in the upper right corner that you'll need to use. So pause, have a go, and then come back and we can check. All right, so if you had a go, then what you should have found is that as you produce the ice chart, so I initial, C change, E equilibrium, we have almost everything we need. Actually, we have everything we need to fill out the ice chart. So we've got 0, we've got approximately 0, the change minus x. Well, the coefficients are 1 to 1 to 1, so that's very easy. And at equilibrium, it's 0.1 minus x, and x, and x. And this is a Ka reaction. So Ka is equal to the concentration of products over reactants at equilibrium. Remember, water's a pure liquid, so we leave it off. And the problem is, right, we don't know Ka. So we have everything else, but we don't have Ka. So everything else here would be x times x, so that's x squared over 0.1 minus x. And if you look at the top right-hand corner at the table, right, it's for bases, so it gives you Kb. And we can see that there's ammonia right here. And, sorry, yellow's not very good. And ammonia has a Kb of 1.76 times 10 to the minus 5. In fact, I'm going to round that and say Kb for ammonia is 1.8 times 10 to the minus 5. And we need Ka for not ammonia, because ammonia is not an acid, but ammonium. That's the conjugate acid to the base ammonia. So how do we get that? All right, well, if you remember in the last section, right, we showed that Ka and Kb are equal to Kw. So if you've got a conjugate acid-base pair, if you know Ka for one of them, you can figure out Kb for the other, and vice versa. So if we want to know Ka, that's just equal to Kw over Kb. And at room temperature, if we're not told, otherwise we're going to assume at room temperature, Kw is 1 times 10 to the minus 14. So then if we go ahead and we do our math, we get Ka for the ammonium ion. And Ka for the ammonium ion, I get to be 5.6 times 10 to the minus 10. So it's not going to be a very strong acid at all. All right, so now we get to put this up here. So 5.6 times 10 to the minus 10. In my calculations, I'm actually going to use the unrounded number on my calculator. And just because I'm a little bit worried about round off error. All right, that's a quadratic equation, but we can make the approximation that x is much smaller than 0.1. And we'll need to check that in a minute, but that's going to make the math so much easier. So then x squared is just 0.1 times 5.6 times 10 to the minus 10. So that's 5.6 times 10 to the minus 11. And if we square root both sides, then we get x. So x, I get to be 7.5 times 10 to the minus 6. And we wanted to know the pH. And so x is the concentration of hydronium ion, and the pH, remember, is the negative log of that. So it's the negative log of x, right? Because x is essentially the H plus concentration. And since we know x to 2 significant figures, we know the pH to 2 decimal places, and I get 4.13. And that sort of makes sense, right? Because if we think it's an acidic compound at room temperature, that means that the pH is likely to be less than 7. So, all right, did you get it? Hope so. Good job.